So now I want to show you a program that I really like. It's called Virtual Fit. I don't know if you see here, I have a folder which I downloaded from the internet. The URL is here on the back, but I will also email it to you so you can see the URL. In any case, once you have there, you download this program into your computer. It's called Virtual Fit, and it has all these applications, all these Java files, and you need to go to the one that says Virtual Fit class. When you click in there, a little console on the side opens, and then here it says start. We click again, and now this window becomes active. And here you notice several things. First, they have a linear function you can fit. They also have a quadratic exponential, an exponential with intercept, and logistic regression. And what I like about it is that you can generate different data sets. You can find the true population, like what will be if you had entire population. You have the least square regression line, and you can play with the parameters for each value. For example, here A and the B, you can move each of those to fit the line. And I like sample size a little larger than 25. It's normally better to see, and I recommend my students whenever we fit data, it's better to have a larger sample size. So let's go with 80. And now we see that this data set doesn't go to the y-intercept, but still we need to fit a line, so we need both values, the y-intercept. So we cannot guess where the y-intercept fits into, and then we move the slope according to the tildedness we want. And I don't know if you notice this, but when I'm moving this line, you see the sum of the squares. It's not the SE, and I know it's hard to understand that, but the sum of the squares, basically how big the distance from the points to the line, if you take the square distances, it is. So we see here is 19, and I think I like to move it a little bit higher up, and then tilde a little more, maybe a little fit, see if I can get it smaller. I didn't improve too much, so I will leave it there. 19.41 is my sum of the squares, and so this is the intercept is 17.96, and the slope is negative 4.1. And so we can also describe the parameters here. So we can fit the least square regression line, and you can see the red line in here. We can make it bigger, and you can see now here on the left hand side we have my answer, which was in black, which is the intercept and the slope and the sum of squares. And here is the least square regression line, which basically is the mathematical way. Now my way is, I say, the I way to do it, by eyeballing it. And this is the mathematical way, which minimizes by mathematics the smallest distances, and we see here that it went down to 18, the sum of the squares. So it's not too far off, so I'm proud of my own fitting. And we can also figure out the true population. This may not be from us 75 students because they don't understand the difference between population and sample, but if for you want to see if you had entire population, this program actually takes the sample from the population, so they can also fit the line from the population. And you see the three of them are very close together, and in the side you have the black line, the least square regression line, and the true population, and the true population was 18 as the sum of the squares. So eyeballing is good, and also here we can talk about whether the y-intercept makes sense in here, because the data only gets up to here, and so on. There is no context in here, but at least I show you the mathematical and the eyeballing aspect of the fitting the least square regression line. I think I like that. But what I like the most, I think, is the other aspects of this, which is fitting. Let's start with the exponential, since the question that you guys asked was about the regression. So let's see here. See, my applet is misbehaving, I guess. So here, there it is. So exponential, we're going to do the exponential, and now you see the line here is a fit in a line. We can move the values here, and we can move the A and the B. We can see this is not going to fit my data very well. When it's linear, it's a line, it's not an exponential, but we can regenerate data for given exponential data, so we can do that. And we can also try to understand what the parameters means. If you click describe parameters, here you have that the function it is parameterized, meaning that it's using other things to make the curve more accurate. And that's one of the issues you will face with fitting a line for nonlinear regression. There is no one function that will fit this data. There will be many functions to fit and many ways to parameterize it, to define that function, and that creates some of the problems for it. So here, let's play with it a little bit. And here it says B is the rate approach towards A, and here A is the maximum height. So the maximum height of the function we can see is going to be over there, since that's the maximum number of the points. And now here I can see I can move this a little bit, and that maybe again looking at the sum of the squares, this is 95. Let's see if we can move this a little bit there, and then maybe here, there. Oh, 86%, 86.94 is the sum of the squares, and I will go with that. Then I will do the least square regression line, and now I see that my sum of the squares were 86, the sum of the squares were 82, and by looking at this you can see there is not much difference. So again, by playing with this we can see that we're trying to minimize the distance to the line, and so fitting the line, exponential, quadratic, or linear, is just minimizing the distance to the line. And so this is answering only one part of the issues with fitting a line into a model, mathematical model, a statistical model, which is fitting the line. So now there are other issues that may not be described by the sum of the squares or by fitting the line, either by either mathematical equation. And that's, like I say, when we have issues like not equal variance, for example. But I want to show you other things before we go to no equal variance. Let's start with the same data points. And so we find the equation here. We have the A value, the B value, and the sum of the squares. We have the answer for the mathematical, and this is the expression of it, which is A times 1 minus e to the power of minus bx. And so it's an exponential function, and it's not a simple exponential function, but this is the function that fits best these data points. But now there is other two options here, and in here we have A times 1 minus 2 to the power of x divided by xh. And what is xh? We can say describe the parameters in here, and then describe the A is the maximum height as before, but the xh is the value of x, which the function equals a over 2. So there's the function a over 2, and we have to figure out how we move in these things. We move the equation. Now we have the population is still there, so it's easy to figure out that we can match it almost exactly the same. But now we have our value for our A and our xh. And now this is another way to find an exponential function that fit this particular curve. And you see here the sum of the square is 86, and before the sum of the square was also 86.94, and this is 86.23. But of course I have a reference now of the red line, which I didn't have before, so it's a little bit of cheating. And I can do this with a new data set, but I just want to point out that basically there is one more exponential function which has different parameters. You can describe the parameters, and here I say this is the slope of the function at the origin. So if you see here, this is almost like a straight line. Here we can see the slope. So by moving this line here up and down, I can see what the slope changes in there, and that will be another way to define this function. And again, because I have the red line, I will be cheating and using the closest one to that one. But so basically now you have three different functions to fit the same data, and that's one of the main issues I want to point out about fitting a nonlinear regression function. There's no one type of equation that fits the data. There is several equations, even several exponential equations. So we're not dealing with a simple as a equals y equals a plus bx. We're dealing with exponential expressions that according to how we organize our equation, they may be fitting the model a little better. So it's very sophisticated for students to understand that. And so, but I still like it, and I think it's good to do it, especially if we do it with this applet in which they can manipulate things and they can see how things move and what the part of the equations means and so on. So it's a little bit of an idea. There is ways to fit nonlinear regression, but it's not as straightforward as a line. And the one I like the most, and I will talk about the residuals after, but the one I like the most here is the quadratic, because they use parameterization with something that we know, which is the x bar. Let's see, this is a little bit tricky. There it is. The quadratic formula. So now generate the data. Let's generate data. Let's zoom out so we can see the data better. There. So that's the data set, so 80 points. And if you see the equation here is a plus, instead of bx, it has b minus x bar, and c equals x minus x bar squared. So this is a circle. So here, if you describe the parameters, they tell you the c is 1 over r if the concave up, and 1 minus r if it's concave down, where r is the radius of the curvature. And so here we can move the things, and we can see here that by making this smaller and moving the height and also the angle of this, the slope of the function when y equals y bar. So maybe here we need to open up the circle a little bit more. Yes, that looks a little better, maybe even a little more. Yes, and then maybe moving a little bit up. Alright, so I will be happy with that equation. And so here, this equation, I have A, B, and C. It's a little bit backwards than Minitab gives it, so that might be a little bit confusing for the students. But what I'm trying to show in here, that this parameterization is a way to fit the line, and it's a good way to fit it. And here we can see again the least square regression line. The sum of the squares for me was 130, and the sum of squares for them was 76, so I missed the board pretty much. And we can also see the population. So this is how fitted here quadratic equation means and how the parameters are. And this is parameterized, taking in consideration the x bar, which is here marked in the graph. So now, where does the residual come into play in here? And that doesn't come but minimizing the sum of the squares and making the line that fits the line the best. The sum of the residuals give us other issues, like, is it going to be a good predictor once I have the line? So for example, let's start with increasing the x values. So now I have let's do it with linear. I think is better. So we understand linear a little better. They can relate better. Generate. So we have a linear. Zoom out, and we can see for sure that the variance here is small, very small. The data is very clustered, and here is very spread out, and we have a total of 80 points in here. So when I try to fit a line, I can still try to fit a line that minimizes the sum of the squares, yes, by doing it by hand or by doing it by the computer program. We go with that. 21 is my sum of squares, and then I can see the least square regression. I was pretty much on the ball here. All right, so this, however, okay, we minimize the square errors. The C will be the smallest. We fit the line. However, because this here doesn't have equal variance, my predictions will be off. And sometimes in big data sets you cannot see that, and in this case you can see it, but then the residual plots will see it. So the residual plots are good to estimating what happened if you want to make predictions. So I think for linear regression it's very good for them to have it. It's not very difficult. Minitab gives it. But for the nonlinear regression, I think if we can get the idea that we need to fit a line that accommodates for all the variability on the points, will be fantastic. Whether we use this program or something else, I think is enough. And then teach them the mathematical formulas using 2 points if you want to find an equation of the line for a quadratic or exponential or logarithmic function.